All right, so in today's notes, we're going to continue with differential equations. We've done some review on it before, and then we're going to move into some like newer stuff like slope fields and Euler's method for today. You can read all the stuff at the top. A lot of this stuff is review, like what we've defined as a differential equation. I do want to point out a few things here. You'll kind of start to note that a lot of times differential equations, you can see some like implicit differentiation and stuff like that. So if you're kind of concerned about that, go back and review that on your own. But we have talked about all this stuff here in prior notes. The only thing that's kind of new for today is just that word order. And the idea here is the order of a differential equation, just the highest order derivative that we see. So quick amount of review to start with. So like in example number 1, we're supposed to determine whether each function is a solution to the given differential equation. And since I see a second derivative here, that's why we're calling this a second order differential equation. So again, as a review, if something is a solution, if a curve is a solution, then it makes the original differential equation true. So like this only uses the second derivative. So when I'm going through all these examples, all I really need to do is find the second derivative of each function. So the derivative of sine is cosine, and the derivative of cosine is the opposite of sine. So that's the second derivative. So then again, what I would do is I would plug it into the original differential equation. So instead of y prime, I'm just going to go ahead and replace that with what we know it is, negative sine of x. And then we have to subtract y, which is given to us here. Right? It says y is the same thing as the sine of x. And when I simplify that, I get negative 2 sine of x, which is not equal to 0. So this is not a solution. One more example here. Again, we're given this new curve, an exponential one here. So again, we'd have to figure out the second derivative. So here, using our chain rule, right, we get 4e to the negative x times negative 1, which I'm just going to simplify. So then our second derivative, using that same process, is actually just going to be 4e to the negative x. So then plugging that back into the original differential equation is 4e to the negative x, which is the second derivative of y, minus the original function. Is that equal to 0? And here we do get a true statement. So yes, this is a solution. There's one more example here. You can see that example. That curve kind of works its way back up into the next thing we're going to run to. So just go ahead and pause the video here, practice that one on your own, and then I'm going to reveal the answer. So you can go ahead and check your work on that and pause if necessary. So aside from the general solutions, the next thing we move to is what we call a particular solution. Meaning, like, for example, this curve here, if I took it and I just added any constant to it, like let's just call it c. When I start taking the derivatives, that value of c goes away anyway. So all this work would still be true, right? So we have initial or particular solutions. And again, a lot of time it is an initial condition just because, like I said, constants and stuff tend to go away as we take derivatives. So for this example, we're given a new differential equation and want to verify that this thing is a solution. So what we have here, this is our general curve, right? This is a family of of cubic functions. It's an infinite number of curves depending on what c is. So once we verify that family of curves actually is a solution, what if I needed to pick just one of them? So our first step would be verifying that this is a solution. So I look at the original differential equation, and there is the first derivative there. So in my curve here, I need to calculate the first derivative. And again, using just our derivative rules, we get 3cx squared. So what we would need to do is we need to plug it into the original equation. So I'm going to start replacing. So we have x. Now, instead of y prime, it'd be obviously beneficial to replace that with an expression that is also in terms of x. Same thing over here. When I subtract negative 3y, instead of y, we're just going to replace it with what y really is equivalent to, which is c times x cubed. And we want to verify that that's actually equal to 0. So in this case, with a little bit of algebra work, we can see here that, of course, this is going to work. So here, this is an infinite number of curves, so we need to choose just one. So the way that we're going to choose just one of those curves is we're going to make sure that it satisfies the initial condition, or the particular condition. I guess it's not really initial without more context. But what it says here, with this curve, all right, this derivative is a solution, which means this curve is the actual solution curve. That's kind of an awkward way of saying it. I'm sorry. This curve is a solution. We verified it by plugging in its derivative. So this family of curves needs to equal 2 when we substitute the value of negative 3 for x. And it's our job to find that constant. So we can see here that that constant is negative 2/27. So what that would mean then is if we're looking for a particular solution, one specific curve, one curve that would guarantee to satisfy this differential equation would be negative 2/27 x to the third. Pretty much all that has been reviewed, nice warm-up stuff. But what's a little bit new for today is something called slope fields. And what's really kind of like the motivation for this is just kind of reading what I have up top here. Sometimes we can't just do it by hand. Like we've seen that before with like integrals, and sometimes as much as we want to use formulas and analytical work like pencil and paper and rules, sometimes we can't. So what we then would go to is a graphical approach. So just a picture. And the idea here is if we can create a good picture of what the solution would look like, we have other skills to maybe like write an equation for that curve if we can like use some curve fitting ideas here. So again, I'll allow you to read the stuff that is here. Pause the video if you need to. And like just in general, before we actually jump into the example, I just want to show you a picture of a slope field. So like this is a picture of a slope field that I have over here. And we'll come back to this example in a moment. And here what we were looking at is just the slopes of a bunch of points. And the idea here is if I can get a picture of what all of these slopes look like at random points, then I can draw a curve that follows those slopes. So like, for example, just kind of watch this little point here. Like if I start here, the slope is 0. And if I follow these as like little, almost like arrows, it says go to the right here. So I keep going. And now here, see how my slope is changing? It's telling me what path to kind of follow. So like I'm here, it says, okay, keep going up at that. So I can follow these curves. And like, for example, if I was here, I can see here that this little thing says move right or left. So if I go left, now it says, okay, go up a little bit, go up a little bit, go up, go up. So if we can get the slope at every point, then we can look for a curve that would follow those slopes at every point. So the idea here is we have to draw these pictures, and it becomes a little cumbersome. So just for like the first intro, when we do it by hand, we need to sketch a slope field here in example 2 for this differential equation. And just because rather than creating like an entire slope field like we did here, we're just going to focus on like 2 or 3 points just to get the idea of how we're starting to create these slope fields. Then we'll match a few slope fields, and then we'll actually go create a big slope field kind of like this. So just in general, we want a picture of what the solutions could look like here. So what we would need to do for this type of skill is with something as manageable as this. I usually say, let's just make a table. So we're going to need a point, right? And a point in space has an XY value. And then the reason that we're getting an XY value, a point in space, is because we also want the derivative at that point, which is going to be labeled as y prime. So they give us a few points here like negative 1, 1. So I'm just going to fill these into the table. Negative 1, 1. The next point has an x value of 0 and the y value of 1. And the last point is 1, 1. I'm going to go ahead and just kind of scale this pretty simply just so we can start to get a feel for that. So the idea here is at this point, I need to use this equation to get the slope, right? And I should interpret this equation not just y prime, but I can also interpret it at the slope at this point is the same as subtracting the coordinates. So the slope at this point would be negative 1 minus 1, so that slope is negative 2. At the point 0, 1, the slope at that point would be, again, 0 minus 1, which is negative 1. And the slope at 1, 1 would be 0. Now the idea here is that we're going to go draw a very short line segment with that slope at that point. So for example, at the point 1, 1, fairly easy to do. I need to draw a short line segment that has a slope of 0. When it comes to the other line segments, it is going to be hard to do it 100% accurately, which is why first I recommend getting all of the slopes in a table and then analyzing them, because things that I need to look for is the slope of negative 1 should be less steep than a slope of negative 2. And sometimes if you start making slopes without the foresight of how steep you need to make things, if you make negative 1 too steep, like let's say I made negative 1 like this, negative 2 is already really, really, really steep. So when I'm going and looking at your slope fields, I'm not necessarily going to be analyzing the exact slope of the line, but for example, at 0, 1, the slope needs to be negative and it needs to be negative 1. So when you put something in there, like here, the next thing I'm going to look for is when you put a slope at negative 1, positive 1, it should be more negative. So we've created a slope field, and that's a very general idea. If we did that for a ton of points, if we extended this table over and over and over and over, so like if I just choose, some other random points, I would create more and more little line segments, and we'd get a slope field like this. So as we move to the next example, like the idea of creating a slope field and like the overall purpose of this before we actually get to the example is like if I look at this picture, I could easily draw a curve through this slope field that would satisfy kind of like that general or particular solution. And again, the idea here is like if I'm right here, the slope is 0. So I kind of just use these as little arrows and I move forward over here. And it's like, okay, once you're here, start going that way. And then, start going that way. So we kind of just follow these little signposts and I'm able to create what looks like a solution. So that's the idea of working through these slope fields. So in this example, what they've done, somebody's already prepared the entire slope field for a large amount of points. And what we're tasked to do is to figure out which one of these equations were they graphing. So just kind of going backwards here. So things that you would look for, just kind of starting and jumping right in, just analyzing things that are easy. Like if I look at this slope field right here, the slope on the y-axis is always 0. So the slope is 0, and I notice that whenever x is equal to 0. So with that, when I look at the equations, when would my slope always be 0 if x was 0? Well, it has to be this right here. So this graph was a slope field for the differential equation in number 2. That is the only one that would give me the slope of 0 when x is equal to 0. So then like moving forward, you can look for other things like that. And I think zeros are usually kind of like the best ones to look for. So I see all these zeros right here as a slope. And what I'm noticing about those is these zeros are occurring when x and y are the same thing, but just with opposite signs, right? Like right here, this is the point -2, +2. Something like this, this is 0, 0. Something down here, this is 2, -2. So when I look at that, that's clearly indicating this is the slope field for equation 1, because if I took the x and the y coordinate at each point, the rate of change there should be 0, and if they're opposites, they'll always cancel to 0. So then obviously by elimination, we can see things that this must be number 3, but we can see kind of the same idea here. One of the best things to look at here is we can see the slope on the x-axis is 0, so y prime is 0 when y is equal to 0. So in this next example moving forward, trying to actually create like an entire slope field and like kind of like a full problem of the slope field. What are we doing with this? So they give us a first order differential equation. We need to sketch a slope field. And then we also need to use that slope field to sketch a solution that's guaranteed to go through this point, kind of like our particular solution. So again, what I recommend with this, the easiest thing to do is to make a table as I've started it. Now with this table, we're going to make a lot of xy pairs just because we need to make a very large slope field and we need a lot of points there. So setting up your table, this is just one way to do it. You can kind of do it however you want. But when it comes to choosing x values and y values, the main idea here is that we just have to create enough to make a slope field. So like we need a bunch of x's and a bunch of y's. So like a strategy that I normally think about is I just start picking x values. Like I'm just going to start at -3 on the x-axis. Now what you'll notice is for each x value, I'd recommend choosing at least 2 different y values. So like if I'm thinking about scaling this, like here's -3, I want a slope up here and a slope down there, one in each quadrant. So maybe I'll choose a y value of 1 and then just, again, randomly choosing some other y value, maybe like -1. I would do the same thing as I move on to another x value. So I'm going to choose an x value that's a little bit further to the right. And I would choose a random y value in one quadrant and then a different random y value in a third quadrant. And maybe for this one, just to help create a nice slope field, I'm just going to choose a different y value, like 2. So again, here, these are all independent choices because every point needs a slope field. So once you've kind of set up a bunch of points, now you go and analyze the slope at each of them. So just doing a few of these with you. So like at the point -3, 1. So if I continue to scale, like this point right here, -3, -1, what's the slope at that point? So I just go use the equation. So I double x, so -6, and then I add 1, so the slope there is -5. So at that point, then what I would do, again, as I mentioned before, I'd probably create a bunch of slopes before I draw this, but I would need to draw a point that has a slope of -5. Then I would just choose some other points, so like I'm going to move on to this next one at -3, -1. And then, of course, doing the formula for the derivative, we get -6. So at this point here, the slope should be even more steep. And that's what I was mentioning before, that at times it's very difficult to kind of compare those. So what I recommend is kind of getting a bunch of slopes in your table before you actually go and draw this. Now, at this point, just for the sake of my timing video, what I'd want you to do, you can see down here, these are the points that I'm going to create in my table. So you go ahead and add them to your table, and then calculate the slope for each of those points. Pause the video, and then you'll come back and compare. So we've created the slopes at all of those points, and then the process for creating the slope field would be two things. The first thing we would need to do, obviously as I did before, just kind of scaling these. I'm just going to go through each point and place the slope, and just for some foresight, 6 seems to be the steepest, right? +5 and -5 are going to have the same steepness of the line, just going in different directions. So I'm literally just going to go do my best at plotting what these slopes look like. I'm just going to start left to right. So at -3, 1, there's a slope of -5. I'm going to make that pretty steep because it's the second steepest slope that I have. Then at -3, -1, that should be even steeper in the negative direction. -2, 1, we have a slope of -3. And again, I'm just trying to comparatively make these, or relatively make these, more or less steep. So at -2, -1, that's a pretty steep -5. Then we keep moving on. I have the point -2, +2, and the slope there was -2. -1, 1, we have a slope of -1. -1, 2, we have a slope of 0. At 0, 0, we also have a slope of 0. At 1, 1, we have a slope of 3. At 1, 2, we have a slope of 4. At 2, 0, we have a slope, At 2, 0, we have a slope of 4. At 2, 1, we have a slope of 5. So you can start to see this slope field kind of making its way in. So then for what we needed to do, and I just kind of plotted as many of those points as I could, what we need to do then, and maybe I missed a few, that's fine, you can go ahead and plot the rest in. Or if you felt like your slope field was kind of missing things, then you would just go back and simply add points. Like maybe I want to point at 0, 1, and I'll see here that the slope is 1, and then I could go ahead and kind of put those in. But what we need is a curve that goes through the point 1, 1. So here's our curve, and here's the point 1, 1. Now at this point, again, I'm keep coming back to this reference of kind of like treating it as a signpost. It's pointing you in the direction to go to. So if I'm here, I follow this little line segment, this direction. Once I get to this little line segment, it says it says start to go this direction. And I can see like how that would kind of follow this slope field here. I could say maybe a solution would look something like that. It can go through those points. That curve, for instance, like at this point right here, that has a slope of approximately -5. So we don't have an equation for that curve, but we do have the ability to draw it. Now, because drawing is really hard, I do have this Desmos thing prepared, and it should be linked where you're consuming this video. And we can see here that I have a slope grid for the curve that we just created. And this is just a movable point. What we can again see here is like the point tells you, so the point 1, 1 is like right there. So it would tell me to go that direction for a little bit and keep following where that little thing is pointing. So it's kind of hard to see, but you could see that like right here, that little line segment is flat, so it says go right. And then, oh, now you're following that direction and you're following that direction. So a lot of times when we use computers or something to make these slope fields, and I'm just copying and pasting a picture here, obviously they're a lot easier to follow because the line segments are actually going to be perfect. But again, that's our general idea. Is the reason that we're creating this slope field is we get a nice visual of what the curve or the solution curve would look like. Let me just put it on a new page here. So this is the slope field for that equation. So if I had to pick a particular solution through the point 1, 1, as we said was right there, again, we can just start following those little signposts. So we can see that something probably looks quadratic like that. There's another one down here, right? If I kind of follow these slope curves, right? So there's a lot of solutions here, and we're seeing visually what they could look like. So the last idea for today is called Euler's method. And what this is just a mathematical approach to what we just did with our slope field. And here what I'm really emphasizing is this, and I've been saying it a ton throughout today, but the slope's kind of like a little signpost. Go this direction for a little bit and look for the next signpost. Then follow that arrow. Then follow the next one and the next one and the next one. But rather than using slopes, we're actually going to plot the points that are on the curve rather than using slopes to create the curve. So the idea is this. We're trying to plot a solution curve. So the idea is, like in this example here, we're trying to plot this blue curve without the ability of seeing those little slopes and following their arrows. So with this method, what we are going to do, and here I'm just trying to choose like an arbitrary starting point, right? If I need a curve, let's say I'm at this point right here. So we're finding a point, and we're going to start at that point. And since I don't know where it is and it's arbitrary, let's just call it x naught, y naught. So the next point, and at this part of the work, I'm going to split the x and the y coordinates into different work. What we're going to do to get our new x value is we're going to start at the old x value, and we're just going to make a small change to x, and we're going to call that h. So like over here, this is my starting point. I'm going to choose some arbitrarily small distance called h. And really what we're thinking about that, h is just a small change to x. So that h value is going to be consistent, and we want that h value to get smaller and smaller and smaller, right? We'd want that h value, the limit of h, to approach 0. So very similar to like the definition of our derivative, right? So the new x value, super easy. That's what it is, right? So I know what my new x value is, but how do I find my new y value? Well, of course, we're going to use the old y value starting information. We're going to use this formula. We're going to add h times this function, right? And this function, capital F, x of y, again, what that's telling us up here is that's the slope, right? The slope at that point is given by this function. And to calculate the slope at the point, I need to know the x value of the point and the y value of the point. So if I plug in the x and the y value, it'll give me the slope. Now, to see why this works, let's use a little change here. So we said h, that was really just some small change in x. And then we know that slope, right? Just in general, we can kind of interpret that as the change in y over the change in x. So if I rewrite that, the change in y over the change in x, we can kind of see how this would work out to our new y value. So this is always our general formula. I start at a point, we arbitrarily choose a small change, h, and as we'll see in the next example, sometimes that's defined for you. And then to get the new y value, we follow this. So according to that little formula then, after I follow all that information, it's going to give me this new y value. So I have a new x value and a new y value, and that's the next point on my curve. And I would just continue to repeat that process. So then what I would do, I would find a new x value. So I'd start at the old one, and I would make a small change to x just like I did before. So then my new y value, and here I'll pay a little more attention to my subscripts on x and y, I would start at that first y value. And then here when I'm using the slope, I'm using the slope from the point before, right? Because it's kind of telling me where to go. So the point before this was x1, y1. So again, what I would then do, like graphically, is we've made a small change. We'll call that h. And then based off of this formula here, we got the new y value. And just so it doesn't look linear, maybe this change in y was a lot bigger. So then we have another point, and this point is x2, y2. And then before you know it, if we continue to do that process over and over and over again, we can start to fit a curve that would be a solution to this differential equation. So let's go ahead and do one. So this is like a full Euler's method that helps us kind of plot a curve. So we need to use that method to approximate a particular solution to the differential equation passing through this point. So the point that is given for our particular solution, that's going to be our starting value. So So our starting point, maybe that's a better word, not value, but our starting point is 0, 1. So x naught is 0 and y naught is 1. Now my method for this one, just so you're aware, I'm going to get all the coordinates first. And then I'm actually going to use Desmos to create the graph here because the numbers are really small. They're like decimals less than 1. Excuse me. So I'm going to turn off this slope grid and this point and stuff here. And what you're going to notice is I'm going to make a table and we'll just start plotting points one at a time. So I'm going to do a bunch of points and then we'll plot them. So obviously that's what I have. Sorry, I should show you. That's what I have in my table. I'll kind of get it ready. So the first point that we have is 0, 1. And then that'll show up and we'll resize that later. So the next point, so x1, that's easy because it's defined h for us. H is just 0.1, so a tenth. So what we're going to do is start at the old x value and add that little change in x. So we can see here that our new x value is 0.1. So I'll add that to our table. And what we need to do is we need to find the new y value. So our new y value is we start at the old y value. We're going to multiply it by h. And then we need the slope at the previous point. So showing a little extra work on this one, 1 plus 0.1. Now the function f, what that says to do is to take x and subtract y, right? This is f right here. So I'll use the actual coordinates here. So x naught, was 0, y naught was 1. So we go ahead and simplify that. Our new y value is going to be 0.9. So we have the next point in our slope field, or excuse me, not our slope field, but the next point on our particular solution. So we'd keep doing that. We're just going to plot as many points as we can, right? So like our new x value, again, fairly easy. We take the old x value and we add the h value. And we can see here how that would just kind of extend forward. If I just kept doing that over and over and over again. So let's get the new y value, right? So y2, that'd be the old y value plus h, so our value of h, times the function's value at the point before it. So if we're looking at y2, the point before it was x1, y1. So then when we simplify that, y2 should work out to be 0.82. So then that's an ordered pair. So the x value, 0.2, the y value is 0.82. Now what I want you to do at this point, just keep doing that. So pause the video and then continue to calculate the y values for all of these x values up to 0.5. And when you do that, pause the video, come back, and then you'll see the answers, obviously. After you've paused the video, what we can see here is if I put in those x values, the y values that you should have gotten, so the third y value was 0.758. At 0.4 in x, the y value was 0.7122, with a little rounding, I'm sure. And then the fifth y value, or y sub 5, was 0.68098. And like I said, I did a bunch of rounding there. So we're starting to get a picture then of what our particular solution would look like. And here's my work for that. So then what we could easily do, like if I were to take a picture of this and add it to my notes, the idea here is this is a picture of the solution. When we did a slope field, we had to draw the solution through the slope field. But here, we've actually just drawn the particular solution. And since we started at a certain point, this is our particular solution and not a general solution. So if I had to get an image of what I think this looks like, it's going to look something like this. And the more information I would want, I would just continue to plot more and more and more points. So this is a particular solution. And then just to summarize the video for today, just because I have the foresight and I know what the actual answer is, that's what I have down here. If I put that in, it's not perfect because my value of h was an approximation. 1/10 isn't really that small. But we can see here that my estimate using Euler's method does fit the curve pretty good. And like I said, this curve actually is the solution. And that was just given to me by a textbook. I looked it up. So there's no way that you would need to know it. But that's what Euler's method is. And there's just a little kind of fact for you here. That's nothing that's usually tested or important. It's just a fact that our textbook throws in there.